I'm Dan Sweeney from MathSpec Incorporated. In this video, I will demonstrate how our Excel add-in can help identify an unknown compound from its accurate mass MSMS data by using substructure searching. Substructure searching is most useful when the unknown analyte that we wish to identify is a known compound that is probably found in the Pubchem Compound database. For example, chemical substances found in surface water samples are usually composed of compounds that are commonly used in everyday life, such as pharmaceuticals, personal care products, plastic additives, and agricultural chemicals. Most of these compounds are found in Pubchem Compound. There are two steps involved in this substructure searching approach. First, the accurate mass MS and MSMS data is analyzed with our Excel add-in to generate modular structures. Secondly, if some of the subformulas that are generated correspond to one or two small substructures, the molecular formula and these substructures can be searched against the massive Pubchem Compound database. Emma Ferrer and her co-workers recently developed a non-targeted screening approach for surface water samples. This JAS-MS paper discusses the nuances of developing generic LCMS conditions with data-dependent acquisition. The mass spectral data obtained was then screened against a database of about 250,000 common small molecules stored in a database as partitions of their molecular mass. 30,000 of these MSMS spectra were imported into an Access database that is freely available on Mendeley. In this video, an analyte that was not in the screening database will be identified using substructure searching with the Excel add-in. The unknown analyte was archived in Microsoft Access with a retention time of 9.95 minutes and an accurate mass of 392.1454 Daltons. It had been selected as a precursor in 3 different surface water samples and fragmented at 2 collision energies. Above is the MSMS data for the wastewater treatment plant A sample at the lower collision energy. In the approach that was described in the paper, the isotope pattern and the accurate mass of the precursor were derived from the MS full scan spectrum, while the masses and intensities of the 11 largest fragment ions were collected from the corresponding MSMS spectrum. Now the first step is to analyze the mass spectral data with our Excel add-in. This add-in generates modular structures, which are rough approximations of the molecular structure. I've opened up a new Excel workbook, and in sheet 1 I've imported the mass spectral data. To generate the modular structures, I'm going to click on add-ins, and then the icon on the right, if I click on that, it will open up worksheets that I need to do the partitioning process. I'm going to expand this. It opens up on the data input worksheet. We go back to sheet 1, and I'm going to copy the mass intensity data and paste it into columns A and B. Go back to here, copy that. This is the isotope data. Generally, the default is positive ion, but you can change it if you need to. I don't know much about this compound, so I'm going to check that odd electron fragment and subfragment ions are certainly okay. I'm going to leave fluorine at 0 just to cut down on the number of hits and in a way take a chance that there's no fluorine in this unknown. The mass error window is 3 millidaltons, so this is saying that all of my fragment ions and subfragments should be within 3 millidaltons of their theoretical value. The maximum isotope ratio error is 9%, and that's an absolute error, so that would allow anything from, in this case here, the 21 would be anywhere from 12 to 30. And subfragment formula restriction, if I had allowed fluorines, then I'd probably use a high restriction on uncommon formulas. If I click on transform, that will start the analysis. While that analysis is running, I'll describe briefly how the Excel add-in works. An analyte is fragmented in the mass spectrometer. Now, some of these fragment ions could be viewed as being composed of smaller subfragments. We would like to first find the masses of these subfragments. There are 3 types of possible subfragment masses: neutralized fragment ions, simple differences, and some mass differences. These can be obtained by addition and subtraction. For a mass spectrum like this one with 12 ions, there will be 298 of these masses and mass differences. The Excel add-in then checks for sets of 3, 4, or 5 masses that sum up to the mass of the precursor molecule. These are partitions of the molecular mass. This operation is very CPU intensive. The subfragment masses that comprise partitions are then converted into combinations of atoms in such a way that all atoms that comprise the molecular formula of the whole molecule are allocated into subsets of 3, 4, or 5 groups of atoms. Each atom of the molecular formula can be found in one and only one subset. This subset is what we call a subformula. Lastly, possible spatial alignments are also assigned based on logic tables, and that results in modular structures. Now, some of the smaller subformulas of the molecular structure may correspond to only 1 or 2 corresponding substructures of molecules. We can use these substructures for substructure searching in Pubchem or ChemSpider. We can go over to data input, and we see that it took 64 seconds to do the analysis. Go back to partition 1. Now the partition scores decrease as we go across. So number 6 has only 59. The scores are based, these scores are based on which fragments are assigned by this particular set of numbers here, and the intensity of those, the relative intensities. So if we look at the next one, it's a little bit lower. The next 2 are a little bit lower. The upper graph kind of shows that this 239 is more than half of the molecule is in one subfragment, which is kind of bad from the standpoint of it's going to give us multiple possible formulas, whereas the small ones have only, in this case, the 4 small ones have only one formula piece. If we look at the next one, it's a similar story. We have a different formulas, but for a particular number, they're all going to be the same. But basically, the mass to formula is not a one-to-one relationship. It's a one-to-many relationship. So in this case, with a 239, we get 3 all the time. And the next one is also the same. And it's the same 3 formulas. So I'll go back to partition 1, and these formulas of the whole molecule are hyperlinks to Pubchem. So I'm going to click on that. It says that there's 102 compounds with that formula. Okay, now frequently I get this problem where there's no query, so it won't let me put more in there. So what I'm going to do to get around this, it's irritating, I'm just going to search for aspirin. Okay, so that'll start, and now I can go back. I don't know why that is. I think it's a bug in the Pubchem software. So now we're getting these 102 compounds, and it will now take those, do the next formula, and there's 22 compounds here. Go to the third one. And there's 3. Now some of these are composites of several individual molecules, so these are not going to work, but this one possibly could be our unknown compound. If we go to advanced, not going to worry about the aspirin, but I'm going to combine these 3 together. So I add them into the builder part up here, 2, 3, and 4. And I want to say or because I don't know which, the compound is probably in one of those 3 sets, but I don't know which set. So I'm going to say or, and we'll combine these 125, it looks like. So we have 127. I guess my math wasn't too good. Go back here, and from previous work I know that CHNO, which is found in a great number of compounds, is not going to work for subfragment searching because we're limited to 1 million compounds, and that will exceed our 1 million. So I'm going to go to partition 2, where subfragment 5 is connected to 3, at least in one of the alignments. I think in the other alignment, everything is connected to the white thing. So I'll assume that that alignment 1, that this is a methyl ester, and it makes more sense than a carbonyl, on the end, sort of hanging out there. So I'm going to go back to Pubchem, go to advanced, back to home, chemical search, draw structure. I'll start with the double bond and the carbonyl, and we can grow off that and put the methyl ester in. Now an important thing to do is to block off this carbon. If we don't, it'll grow. It'll grow out here. The Pubchem will take it'll take ethyls, propyls, anything. So we want to block it. So we actually have to draw in the hydrogens. So now the only place that this is going to be a substructure of a larger molecule. It can only attach to that at this position here. We'll do the hydroxy. And again, change this into a hydrogen. So this will connect out here. Search for this. We want to do substructures. It found 1,000, and it only searched a very small portion of Pubchem. Pubchem has over 100 million compounds. If I go to settings, I can see why it only did a small part. When it removes those hydrogens that we use to block, that is the default setting, so I want to get rid of that. And we don't have any rings to worry about with those substructures, and we don't have to worry about aromatics with those either. So now we've reset the default settings. We've changed the default settings, and we want to search the entire 100 million compounds, over 100 million. Okay, so we get 758,000 methyl esters. This is a good example. Methyl salicylate, we've got the methyl ester and the hydroxy. I want to push these over to Entrance. That's where our chemical searches went. And now we have these 758,000. I'll go back to advanced where we can do the unions and intersections. I want to add 2, 3, and 4. This was our combination of all those formulas. And this is a combination. It can only do 100,000 at a time. So number 14 is the substructure search. And whatever works has got to be in both. It has to have one of those 3 formulas, and it has to have those substructures. So now search that. So now we have 9 possible structures that we need to look at one at a time to see which of these may fit our modular structure. If we bring that up, this is our second modular structure that we did the substructure searching on. We could have also looked at them one at a time with just the formulas without the substructure searching, but that was 127 compounds, and this is only 9. So the substructure searching in this case has helped a lot to reduce the search space. So it appears that this compound called hydroxy-Y base actually seems to work really well with the modular structures. Number 2 that we had, it's almost a perfect fit. It was found in a wastewater treatment plant A. If we look at Y-butazine, this is a related compound. It doesn't have the hydroxy in here, but this is a component of transfer RNA, and this would account for perhaps from people eating food that has tRNA and transfer RNA, which is probably everything. This could account for why that would be in a surface water, several surface water samples. So in summary, substructure searching is excellent for unknown analytes with little or no background information. It requires partitions that have small subfragments that can be directly correlated with substructures. But it has limited usefulness. The entire Pubchem database must be searched, and the maximum number of hits is often reached.